Hi, year 12s. I just wanted to go over a few key points from the end of last week and this week's work. Okay, so I'm going to first focus on simplifying before differentiating. And when you ask for a gradient at a point, you need to differentiate before you do any substituting of the point. We've got some nice notation to make it very efficient. And if you have a graphics calculator, I'll show you how you can use that to check your answer. Okay. So let's start with an example. So if we want to find the gradient of the curve y is x plus 2 over root x at the point where x is 2. Okay, so we want to find the gradient, so that tells us to differentiate. So working out dy by dx. And we want to work that out where x is 2. So we're going to be finding out dy by dx at x equals 2. And so writing that vertical line there just tells us we're working it out at one point rather than the general formula. Okay. Now before we can differentiate, we need to simplify this to get it into a form that has lots of x to the power n's in it. Because we have a rule for differentiating this, but not for differentiating brackets, roots, etc. Okay. So let's look at this one. Now the problem is this 1 over root x. Okay, so we could write y as 1 over root x multiplied by x plus 2. Okay, so this is x to the half on the denominator, and because it's in the denominator, we write x to the negative a half. Okay, and then we need to expand brackets. You'll learn a rule in year 13 that helps you with brackets, but this is what we do in year 12, we always expand the brackets. So we've got x to the negative a half times x to an invisible power 1, and we add the powers, which is x to the half. And then we've got x to the negative a half times by 2. Okay, slightly smudged that, never mind. Okay, so now we're in a position where we can differentiate this. We've got x to the n plus something x to the n. Okay, so let's start with x to the half. So we bring the power down, we multiply by x, and we reduce the power by 1. So a half take away 1 is negative a half. Then we've got plus, we've got 2 times x to the negative a half. So bring the power down, we write x, and then we reduce the power by 1, so we get negative 3 over 2 there. And let's just tidy that up. So we've got a half times x to the minus a half, and then we've got 2 times negative a half, so that's negative 1, x to the negative 3 over 2. Okay. Now if we wanted to, because it helps us think, we could then write that in terms of roots and fractions. So if you did that, you'd have 1 over, now we've got a negative power, so it'd be 2 root x. Take away, and then 1 over x to the 3 over 2, so that's x to the power 1 times x to the half. Okay, but I don't think that's going to hugely help us at this point, because we just need to now substitute in a number, and we can type that on our calculators, no bother. Okay? So I'm now going to work it out at 2. So I just write equals, and I substitute wherever I see an x, I'm going to put 2 in there. You can see that if you had to kind of do this by hand, then converting it into the root form would be easier. Okay, I'm going to get my calculator. Now I have a graphics calculator, so if you're using that, it's just slightly different the way you type the fractions, but I'm sure you'll be fine with it. So we've got half, so I press the ABC button and fill it in. Okay, times 2, okay, to the power, so that's the little hat button, and then negative a half. Okay, and then minus 2 again to the negative 3 over 2. Alright, and that gives us 0, which is rather nice. If we worked it out here, we'd have 1 over 2 root 2, take away 1 over 2 root 2. So that makes sense, it gives us 0. Okay? Right, on your calculator you can do it all in one go, and it's a bit like this notation here. So I'm in the Run Math menu, okay, and at the top I can see there's just above F4 there's Math, so I press F4 and look at my math options, and one of them is d by dx, so that's differentiating, and so we've got d by dx of this thing at this point. Okay, so I can type in the original y, so I can type in x plus 2, okay, over root x. So the x that I'm using is just, let me show you, sorry, it's just below the alpha button. It's the one with x, theta and t, and that's used for variables, okay? And I want to work that out, so I just keep pressing the arrows till I get onto the equals bit, at x is 2. So then we execute, and it is 0, so I've got it right. Well done, me. Okay, the next thing we're going to look at is increasing and decreasing functions versus positive and negative functions. So I wanted to just make sure this is really clear. Right, so here we have a graph of a cubic function, and I've attempted to copy it, but it's gone a bit wobbly, but there we go for the second one. Now we have to read really carefully in different questions about whether they're asking whether our function is positive or whether our function is increasing. So positive function, that just means we're looking above the x-axis. So this function here is positive all the way there. Alright, so that's just above the x-axis. So we would write down, if we read positive function, then we would write down f of x is greater than 0 or y is greater than 0. Okay? And if we were asked about where the function is negative, then that is below the x-axis, so the only bit of function negative is this bit here. Okay, so in that case we are looking at where the y values are less than 0, so when the function is less than 0 and the y values are less than 0. Now if instead it says where the function is increasing, that means it's getting bigger, it's going uphill. Okay, so we want to look at where is it going uphill. So it's going uphill for here up to the maximum, and then from the minimum and up. And so that is where the gradient is positive. Okay, so we wouldn't write down f of x is greater than 0, we'd write the gradient is greater than 0, or we could write dy by dx is greater than 0. So as soon as you read those words, that tells you what maths to write down, and then that helps you because you know how to deal with the maths. In contrast, if it says we've got a decreasing function, that means it's going downhill. So in this case it's from the positive down to the negative part of that curve. Okay, and we have got the gradient, okay, not the original function, the gradient will be negative. So you could either have f dashed x is negative or dy by dx is negative. So just be careful not to mix those up. Okay, so our next point is thinking about rate of change of something. So if it says the rate of change of p with respect to q, then we write dp over dq. Like the gradient is the rate of change of y with respect to x, dy over dx. If it just says the rate of change of something, so the rate of change of weight, that means how does it change through time? And so that would always be over dt. Okay, so if it doesn't mention with respect to, which we shorten to WRT because it's too annoying to write, if it doesn't say that, just do it with respect to time. Okay, right, and then the final point is looking at using different letters and variables versus constants. So with our y and x are variables, and then we usually have numbers with them. So let's just have a little look at this example. So starting off with just a nice friendly y and x, we say that x is our variable here. Okay, y is a different variable. that depends on x, and then these values 3 and 7 and 8 never change. So 3 is always 3, 7 is always 7, 8 is always 8. So it's not varying, there's no like rate of change for it. So they're called constants. Okay, so I've underlined in pink the constants, a bit vague there, and I've underlined in orange the variables. Okay, and we know that y is dependent variable. So if we're doing dy by dx, we know what we're doing. We've got 3 times, we bring the power down, 2x to the power 1, plus 7 times x to the power 1, we bring the power down, 1, x to 0, so it's just 7. And then when we differentiate this one, remember it's like having x to 0 there. Okay, so we bring the power 0 down, we've got 0. So I've kind of spelt it out, but you know, you could probably do it in your heads now, that this will be 6x plus 7. Okay, right, so let's just do the same but with different letters. So this time we've got our dependent variable is q, it's a bit messy, sorry. Okay, and our independent variable, the one that we differentiate with respect to, is p. Okay, so when we've got q, in terms of p, we do dq on the top, so the one on its own goes on the top, and the one that we've got loads of stuff for goes underneath. That's our with respect to. And again, we've got these numbers that never change, so they don't need to be involved in the differentiation, we just multiply by them. Okay, those are our constants. Okay, so that then gives us, let's have a look, we bring the power down, so we've got 3 times 2p, okay, and then 7 on its own. Okay, right, so now what happens if we introduce some more letters? Okay, so the letter on its own on one side is q, so we're going to start with that. And let's say we want to find the rate of change with respect to p. Then that means, because it could have been, really, it could have been any of those letters, so you've got to read the question. It says with respect to p. So p is our variable. And all of the other letters are just constants. They're not going to change. Okay, they're not changing at all. So we don't care about those. We're going to treat them just the same as if they were a number. So if it helps you in your head, then just pretend that A is like 9 and B is 6 and T is 4. Just pretend they're numbers and then it should all work out. So let's just spell this one out. So I've got this number A multiplied by, and when I differentiate p squared, I get 2p. Plus, I've got this number b, and when I differentiate p to the 1, I get 1. And then I've got this number t, which is like t times p to the 0, so that just becomes 0. Remember, when you differentiated it, you got 0. Okay, so when you differentiate the number, the constant t, you get 0. So if I just slightly tidy that up, we've got 2ap plus b. Alright, so pretend all the other letters are numbers and you should be